Okay, time for a quiz. Simple quiz. You're going to love this one. We said the transformation between two images taken from the same center of projection is a homography H. How many pairs of corresponding points do I need to compute H? A, 6, B, 4, C, 2, D, 8. Right? And everybody's going to say 8 because it's 8 degrees of freedom. No, it's 4. It's 4 pairs of points. Each pair of corresponding point gives you 2 equations. So you'll remember that. There are 2 more things I want to show you. One is just some nice little mathematics to explain to you about homographies and planes. And the second is some of the cool things we can do with homographies and planes besides just mosaics. So let me show you a simple proof, if you will, or demonstration about this 8 degrees of freedom being a mapping between any planes. So let's go back to our calibration from the external world to the internal world. So you remember this? Right, XYZ1 is mapped through a 3×4 homogeneous matrix, or I should say it's a matrix, but we're doing this homogeneously, to get out the projectively similar UV1 over there. And remember we talked about solving for all the 12 M's using lots of extrinsic points. But suppose, just suppose, all the points in the world were lying on a plane. So you might remember from your algebra that simple equation of the plane, AX plus BY plus CZ equals D. Right? So that's the equation of a plane. Basically what it says is it gives me the normal to the plane and where along that normal the plane has to be. What this equation means is that I could solve for Z in terms of X and Y and A, B, C, and D, and I could plug that in. And that's what we did here. Here we removed Z and put in its equivalent expression in terms of X, Y, and then the A, B, C, and D, which define the plane. And so now it's the same M matrix that we had before, but we've gotten rid of the Z. But wait, if I have only X, Y, and a constant in this term for Z, I can put all the influence of this column, 0, 2, 1, 2, and 2, 2 of M, I can put that in these other coefficients. Right? I don't actually need this column since that's just multiplying the terms that have the x, y's, and the constants in them. I can put all the effect into those other 3 columns. So when I do that, it looks like this. Okay? And you'll notice I now have a column of zeros here. Okay? So that's really not doing very much. I just have these 3 columns multiplying x, y, and 1. All right? But that's just a 3×3. That's my homography, okay? That's why the mapping from any plane to any plane can be done by a 3×3 from a location on one plane to a location on the image plane, and so basically between any planes. In fact, a way of thinking about that is this, right? Mapping between planes is homography. You give me 4 points on this plane and 4 points on that plane, I now know how all the other points on the plane map to each other. And whether it's between a plane in the world and an image plane or just thinking about it between arbitrary planes, that's the warping that it takes in order to do this homography or projective projection warp between the planes. And mapping between planes is something we do a lot in computer vision, which is why these homographies show up quite a bit. We're going to do even more sort of sophisticated way of thinking about lines and planes in the next lecture, where we do even more about projective geometry. Got it? Cool. What else can we do? Well, if I can warp between planes, arbitrary planes, that means that I can take planes that, say, are in some particular orientation and think about what would they look like turned in a different orientation. So here we have a situation where we've got a plane. It's the side of this building. I'm going to assume the building is more or less planar. And I'd like to rectify that. That is, I want to remove the slant. So you see this window here? All right, you see how if I were to extend out, these are vanishing point lines. All right, so these are not parallel. They're going to converge. You can see that here. They'll converge all the way out there. All right. But if it was frontal parallel, then they would remain as parallel lines. Well, if we could compute the relationship between this quadrilateral, which is essentially like a trapezoid, between that and a rectangle, we would be able to rectify the entire building. And in fact, that would look like this. At which point you're supposed to say, ooh, that's cool.
Ooh, that's cool.
Very good. So here's the corrected image where now everything is rectilinear. And in fact, if you take a look at these windows, in fact, notice that these are sort of narrow windows here and wide windows here and narrow windows there. If you want to think about that from a measurement perspective, you can see that the windows that are sort of 2 panes wide were narrower than the ones that are 3 panes wide, even though clearly this is wider than this in the image, but when I rectified it, I was able to measure the whole thing. Show you another example of that. So here's a picture. Suppose you want to measure something, let's say start with on the floor, okay, so something about across what's on the floor. Well, they have tiles, and those tiles are actually rectangles. So I could unwarp this picture so that those tiles are now squares, because they're, let's say, 9 by 9 inch squares, which is some number of centimeters. 9 times 2.54, say 18 to 4, I don't know, 23, 24 centimeters. Anyway, I can rectify that image, and then I could go ahead and I could measure in that new image directly about the tiles. Likewise, if I wanted to measure something on the side of this wall, and that's a planar surface also, it happens to be very skewed, I could rectify that. And here, I've taken that wall and I've spread it back out to being rectangular. Actually, I didn't. The person I stole the slide from did. And I could now measure on that. And what kind of warp is this? What kind of transformation? Plane to a plane? That's right. It's your friend, the homography. Just to show you what I was talking about from not from quadrilaterals to rectangles, here on the left-hand side, I've identified 4 points. And you can see those 4 points are the 4 corners of a 2 by 2 tile matrix, but of course the points aren't rectangular because of perspective foreshortening, right? But I can warp that to being a regular square or rectangle, and the rest of the image will come along for the ride. Turns out that there are some other rectangular grids. It's really nice when somebody spray paints the rectangular grid. Here you're seeing a movie of a American football play. In fact, this is a college football play. But you'll notice they're running around on a plane, because to play football on bumpy things is hard. All right? So since it's a plane, we can rectify that to a different plane. In particular, what about the plane that you would see if you're looking sort of overhead? Okay? So what we've done is, this is just the same frame mapped to a different view where we've taken these lines which converge and we've made them all parallel. All right? Now you'll notice all the points go to the right place, except the players, of course, right? They are not on a plane. Just their feet are on the plane. So the feet go to the right place, but the players themselves are stretched out because the players are not on the plane. But what we did is we applied the entire homography, we applied the homography to the entire image, so everything on the football field went to the right place, the players went to a slightly different place. But you'll notice if you look at this, you could see exactly what's going on. Here you see 2 videos playing at the same time. One is the play as observed by the camera. The other one is this rectified thing. A little bit of shaking is going on here because this was done all automatically. And by the way, this is like one of the few results I'll show you that was actually done by a student of mine when we were doing about interpreting American football plays, and this was just a pre-processing step. But we're able to recover the projection. So if you need to save money on a blimp, this is what you do, so you can see an overhead view. In fact, in some sense, this is easier because you see the side of the players, not just their overhead. So I probably should have patented this and made $1 billion, and then well, it didn't happen. We've kept talking about warping images from one to another. That is, we take an image, we pump it through, is the phrase I've been using, or we transform it by homography, which means we have to go and transform this image. We have to warp this image. So the question is, how do we do that? The answer is there are 2 ways, the forward and backward. And there's another word for those, the wrong way and the right way. Image warping can be thought of this way. Suppose I have an image transformation, and I have some source image, f of x, y, and I know how that maps to x prime, y prime. Or another way of thinking of it, I know how that maps in the other image. I'm going to create some new image G, and for every x prime, y prime in it, or call it a and b or ij, what value should go there? And this t of xy is the transformation that says, given xy in one image, that value should go to x prime, y prime in the second image. So forward warping works as follows. you basically send every pixel f of xy, so I've got the first image, it's at xy, I send it to its corresponding location in the second image. So I have some pixel here, a little red dot, I know where it goes, and I put that same color that was down on the first image down in the second image. And that's okay, but you might ask the question, well, what happens if this pixel lands between pixels in the new image? Let's take a look at that. So here's a picture, and I credit Alyosha Efros about this. And in this picture, let's assume that the lines are exactly, you know, y equal 2, y equals 3, and x equals 14, and x equals 15. So the intersections of the lines are the precise pixels. So if I have a pixel here, and I map it across, I may land somewhere between a pixel, okay? And somehow what I have to do is I have to take the color that came from this location, and I have to distribute it among all the pixels that are around where I landed. In graphics, that's known as splatting. That's the technical term. I mean, I guess it's the idea if you threw some paint down there and all the paint had to drain out to its neighbors, where would that paint all land? And that's sort of an annoying way of doing things, and that's why I said that that was the wrong way of doing warping. The right way is what's known as inverse warping. Given some pixel in x prime, y prime in the new place, transform back, figure out where it came from. So now xy is the inverse, t inverse of x prime, y prime in the first image, right? So I have to figure out where it came from. So I have a pixel on the right, I figure out where it came from in the left. Now you have a different question to ask. You no longer ask question, what happens if I get sent to a location between pixels? I now have to ask the question, okay, what happens if a pixel comes from between two pixels? Well, what you have to do is what's referred to as interpolation. Interpolation basically says, if I have some set of pixels, and I'll think of them as being at integer locations, so I have some pixels here at the corner, and I wrote that as ij, I plus 1j, ij plus 1, and I plus 1j plus 1. So those are the corners. If I want to find the value of something that is, say, a distance in x between the two pixels, and b distance or b percentage in y between the two pixels, what's the value? The general process of determining what the value of a function should be between points that you know is referred to as interpolation. Here we're back to thinking of our images as functions a little bit. So we have a value of the function at each of those integer locations, and we need to guess the value of the function at this location that's somewhere between the points we know. That general process is referred to as interpolation. The simplest interpolation is called nearest neighbor. Nearest neighbor means, well, just like it sounds. I land someplace in my grid, and I say, oh, you're the closest value. I'm just going to pretend that I'm that value. So this quadrant would all have one value. This quadrant would have another value, etc. It's not a very clever, not a very smooth way of doing things. A much better way, and perhaps the simplest computational way, is called bilinear interpolation. Bilinear interpolation basically says that I figure out the value in the x direction along both the top and the bottom, and I do that by linearly interpolating between those two values, and then I would interpolate between those values again using a different proportion, in this case b. Because these are all linear operations, you can just write it as one single linear operation, and you get this formula here. And it's very clean and very easy. There are more clever ways, by cubic, where you take, instead of just fitting linear things, you fit cubic splines between them. But basically the idea is that you're interpolating. And what's nice now is that you don't have any holes in your picture, right? You went for every pixel in the target image, figure out where it came from in your source image, interpolate that value, and stick it in the target image. So there are no holes in your warped target. By the way, it won't surprise you that MATLAB and OpenCV and Octave and all these supports this interpolation generically. In MATLAB, you can take a look at this function called interp2. That's two-dimensional interpolation, and it will allow you to do this. All right, so just to review a little bit, we talked about sort of a practical application about how to make a mosaic or a panorama. We said you take a bunch of pictures from the same center of projection, same camera position. You compute the transformation between each of the images, say the first and second, right? What's that transformation going to be? Well, same center of projection is going to be homography. You then use that homography to transform, say, the first image to align with the second. There'll be some overlap, so you'll have to blend them, and then you can continue to do that. So that